Chapter 28 is about microelectronic fabrication. So we learned about machining, and that's the big types of things, the macro products and macro parts that we make, and you've done a lot of that in the shop. Okay, so now we're switching to how do you make very, very small things, and we're going to look at computer chips, right? There's tons of different ways to make small things. We're going to focus on this chapter on making microelectronic and microelectromechanical systems. So those are things that have minimum geometries, 1 micron and less. So you can go all the way down to 7 nanometers now in high volume production for making computer chips. Okay, so we're gonna talk about that. All right. So here's a question. We normally do this with eye clickers. I'm going to go ahead and see if I can see my chat box. Okay. Go ahead and try to answer this question. Who invented the integrated circuit and received the Nobel Prize? So let's see if folks can figure it out. A few of you are jumping right in there. Okay, since you can see the chat from everyone else, it's kind of once one person puts an answer in it, you all follow. But you're right, it's Jack Kilby from Texas Instruments. So the picture you see there is the first integrated circuit. And that was back in 1958. So it's been a while. Jack Kilby did this at Texas Instruments. He got hired on right before Christmas. And at TI, and he didn't have any vacation time. So he went ahead and worked in the labs while everybody else was taking off. And I guess that solitude allowed him to create this integrated circuit device. So it's pretty sloppy. It's made out of semiconductor material. I think he used gallium arsenide the first time. And then later on, they found that silicon works better. So that's what he looks like. Okay, and he's holding one of the first devices. Well, that's the same one. Okay. And I actually shared the Nobel Prize with another fellow for the invention of the transistor. Okay. So this chapter has got a lot of different parts to it, okay? And we're going to go through all of these parts, so it takes a little bit of time to understand. Hopefully the lectures will make the book a little more clear. I know it's kind of tough reading through all of this stuff. Okay, so take your time, but I suggest you start reading the chapter today. Maybe after you finish that that film on machining and chip formation. Okay. So, like I said, we're working with a very small scale. Okay, so you can see the scale here. It starts at the bottom at about an angstrom and it goes up to 10 meters. Okay, and it's trying to show you the relative size differences between different things. So if you're not real familiar with scale and how small things are, this might be worth taking a look at and thinking about. So you can see some examples in nature there, human all the way down to atoms, right? Atoms are typically on the order of an angstrom or so. And humans are up around a couple of meters. Okay, so we're going to be working in the realm of about 10 nanometers to several microns in this region here. Okay, so you can see dust particles are down in the 1 micron and less range. Viruses are actually around, I think 15 nanometers or so. I don't think they get down to, or they're that big, tens of microns. So I think they made a mistake on this graphic. And then you can look at the manufacturing processes to make these small things. So we have to use lithography down in the 1 micron and submicron range. There's really no way to do any kind of machining at that level. All right. So we're going to learn about that. Now, I like this graphic. This shows you some of the different sensors and electronics that are in a car. Okay, so microelectromechanical systems, or MEMS devices, are made of very, very small parts and small components, and they're designed to take environmental information like pressure, temperature, you know, what kind of chemicals are in the air and that sort of thing, and convert it into an electrical signal that your computer systems in your car can react to. So a classic example of a MEMS device is a crash bag sensor, right? So when you hit a wall with your car or hit another car, your car suddenly changes its acceleration in the negative direction, and that results in a sensor noticing that your car is stopping very quickly. And that produces an electrical signal that ignites a small explosive device that's inside your airbag. So the airbag explodes, and before you actually have time to react and hit the windshield. Okay, so that's one of the many different microelectromechanical system sensors that are in your car. Of course, there's other systems in there that are related to navigation, to fuel economy, and those sorts of things. So this is a nice summary of a good chunk of the different sensors that are in your car. Okay, so like I said, you know, earlier on, we have links to the Canopy system online. So I'll post a little more detail on that in the Chapter 28 learning module. Okay. And those videos I suggest you watch between lectures. Okay, there's a real good one called Sand to Silicon by Global Foundries. Do you guys want to watch this video? It's about 10 minutes. Let me see what we got in terms of chats here. No one said no. Okay. All right. So put in the chat box if you can't hear it.
You are about to experience a fascinating journey through the clean rooms of the semiconductor industry. See integrated circuits in the making at one of Global Foundries' chip factories. Let our experts walk you through the nanocosmos of the atom. A world that normally remains hidden from our eyes. In the beginning is the circuit diagram. At design centers around the globe, experts collaborate to design circuit diagrams, sophisticated integrated circuits like microprocessors, high graphic processors, and wireless communications ICs. The next step is manufacturing. The disk substrates for the microchips are made from quartz sand and are called silicon wafers. To make these wafers, a huge monocrystal is drawn from purified silicon melt. The result is a perfect silicon lattice into which the transistors will later be fitted. However, impurities pose a threat to these flawless silicon crystals. Our global foundries manufacturing teams must therefore take extensive precautions every time they enter our dust-free clean rooms. The result? Our wafers are fabricated in an environment that is more than 100,000 times cleaner than an operating theater. Completely free of dust, the silicon discs arrive at the clean room. Here, 25 wafers are packed into each hermetically sealed container and sent off on a journey that will take them through hundreds of manufacturing steps. Photolithographic techniques transfer the circuit structures to the wafers, rather like slide projection. The key to this whole process is a solid mastery of light. The silicon disc is spin-coated with a photosensitive resist. UV light transfers the circuit structures depicted on a mask to the wafer. The exposed parts of the resist are soluble and are removed by a developer. The transferred structures can now be used as a template. The unprotected parts of the water surface are etched away. The structures of billions of small current switches are generated on each wafer, tiny transistors. From the photolithographic stage, wafers move on to the ion implantation, where the electrical properties of the transistors will be specified. Here, the engineers make good use of one of silicon's most important properties. Silicon is a semiconductor, which means that its conductivity can change via a high precision emplacement of so-called dopant atoms. First, dopant atoms are injected into the silicon structures. These atoms then distribute randomly in the silicon lattice. At high temperatures, the doping atoms become flexible and take on a fixed position in the atomic structure. The complexity of manufacturing tiny transistors requires a clean room as big as 2 soccer pitches. While our people monitor the complex processes, automated manufacturing itself always takes place within hermetically sealed production lines. Copper dominates the next process step. The finest interconnect wires link up billions of separate transistors to form integrated circuits. Before that can happen, however, cleaning is essential for wafers, as particles lurk at every stage in the manufacturing process. Before the copper is poured into the trenches for the interconnects, a barrier layer is applied. It helps to avoid short circuits and guarantees reliability. The trenches are then filled with copper. Finally, the excess copper is ground down to the edges of the trenches. This insulates each interconnect from the others. A microchip made of copper wiring established GlobalFoundries as the first company in the world to adopt copper in volume production. A foundation for the state-of-the-art multi-core processors that GlobalFoundries is introducing today in all product areas. To keep us on the leading edge of the world's chip makers, electron microscopes constantly monitor every step in the manufacturing process, down to the atomic structures of each individual transistor. In 2 months, the wafer is ready. Huge integrated circuits consisting of conductors with a length of multiple kilometers link up 100 billion transistors on numerous levels. And that in a space no larger than a fingernail. GlobalFoundries, the first truly global semiconductor foundry, located in the USA and Germany, Fab 1 in Dresden, and the future Fab 2 in Malta, New York. Together, they'll be 2 of the most advanced chip factories on Earth and a testing ground for the very latest microelectronic innovations from around the globe. The last production step in microprocessor manufacturing is the packaging of the chips. In preparation for this step, tin silver pellets are applied on the wafer. They will link the chip to the frame. Via the finest saw blades, the chips are cut off the wafer. The flip chip method is used to bond the chip to the frame, which is sealed with a cover.
Next slide would be, so these are some of the companies, right, that supply microelectromechanical systems. And a lot of these companies are also electronic circuit manufacturers, right? So you can see all the different companies there. And this is a good slide if you're interested in this sort of work. You know, where do you go and apply for a job? So, you know, the microphone systems in the cars are from Knowles, Invisense, those are American companies. TDK, I think, is Japanese. And then for the pressure transducers, we have Bosch. That's probably the #1 MEMS company. Infineon, NXP, and then Intel does some of the imaging and radar systems, as well as Bosch. And you'll see Bosch everywhere in this area. So NXP used to be called Philips Semiconductors back in the day. So they spun off, they recreated themselves, called themselves NXP, and then they started buying MEMS companies. So it was kind of an interesting history with Philips Semiconductors. They used to have a fab in Albuquerque that I worked at. Okay, so you can see there's a lot of different parts in here. And if you go to the Bosch website, they have a lot of good information on microelectromechanical systems. Okay, we got another late arrival. And hopefully we won't get any Zoom bombers today. Anyway, so you get an idea, right? So the work and this chapter will hopefully open up a whole new level of opportunity for you for career paths. This is some of this slide tells you how much money is being spent in just the microelectromechanical systems. So you can see that there's a huge growth in imaging, radars and LiDAR. LiDAR is light radar, basically, instead of radio frequency. It's usually in the infrared. Okay, so different kinds of sensors so the car can see. And then you have chemical sensors and magnetic sensors, pressure sensors, imaging, inertial sensors, ultrasonics. That's also helps navigate. And you can see the growth from 2016 to 2022. It's huge, right? We were spending $11 billion in the sensors, and now it's over 23 billion. It's probably higher than that. These guys usually are pretty conservative on their estimates. And that's just the little widgets. That's the little chips that go into the car. It's not the car itself and the associated electronics. These are just the sensors themselves, okay? I'm gonna open up the chat box. All right, so I'll go ahead and next slide. So here you see what a finished fabricated wafer looks like. This is a 300 millimeter wafer, which is about 12 inches. So the history of wafer sizes, you know, if you go far enough back, we started with very, very small wafers, less than an inch. And then we went into production with 1 inch, 2 inch, 4 inch, 5 inch, 6 inch, 8 inch, and then 12 inch wafers. And they're trying to get 18 inch wafers going, but that's extraordinarily expensive, especially the tooling for it. All right. So this is an 8th generation Intel i7 core processor. This is out of the book. It goes all the way down to 14 nanometer technology, which means the smallest structures that they make on this chip are in the order of 14 nanometers, which is quite small. Okay. Here is a detail of one of the chips themselves. So if you go back to that wafer and you look at one chip, right, it'll look like that. So you can see there's a lot of detail there. A lot of very small parts, billions of transistors. And then this is what it looks like when you put it in a package. Okay, and then once you have your chip in a package, you can put it in a printed circuit board. So this is a motherboard for that chip. And that could go into your laptops and whatnot. So we make computer chips on silicon substrates, and that's pure, ultra pure silicon, okay? And we talked a little bit about crystallography in the previous chapters. The way they make these crystals is they'll melt a whole bunch of pure silicon in a very large crucible, and then on the end of this rod here that you can see, hopefully you can see my cursor. On the end of the rod, they put a seed crystal, and they dip the seed crystal right on the surface of the melt, and then they slowly pull it out over time. Okay, so you can create a crystal that the orientation matches the seed crystal. And depending how fast you pull it out, you can get different wafer sizes. So the graphic on the left shows you what a single crystal looks like when they're done making it. And then they slice it and dice it. Okay, and there's a couple of videos here to watch. Let's see how we're doing on time. Yeah, I guess we can watch one of these. Let's see if this is working.
Of a miniaturized miracle, the silicon chip. And here in Sherman, 20 miles north of Dallas, is the MEMC fabrication facility. In this strange, futuristic-looking plant, they produce silicon wafers, which are the basis for all modern microchips. Silicon has special properties because it's what's called a semiconductor. That means that depending on how it's treated, silicon can either conduct or block the flow of electricity. It's this property that makes it ideal for supporting the millions of tiny transistors necessary for a modern computer chip. But because these transistors are so incredibly small, the silicon base on which they rest needs to be absolutely flawless. It took decades to perfect the process of producing silicon with a perfect monocrystalline structure. They begin with raw polysilicon, or poly, and heat it to over 2,500 degrees Fahrenheit inside a special sealed furnace, which has been purged with argon gas to eliminate any air. The resulting lake of molten silicon is then spun in a crucible, and a silicon seed crystal, roughly the size and shape of a pencil, is lowered into it while spinning in the opposite direction. As the molten polysilicon is allowed to cool, the seed crystal is slowly withdrawn at around 1.5 millimeters a minute. The result is a single silicon crystal weighing around 440 pounds and with a diameter of around 200 millimeters. The crystal is so strong its entire weight can be supported by a single thread just 3 millimeters across. But it is brittle, and it must now be cut down to size without shattering. After testing with chemicals and 99% pure. Once cut, there are microscopic marks left on the wafer surface, so it's time for a buffing using a process called lapping. After a twirl in this high-powered polisher, they are still not smooth enough. So they're given yet another buff using a chemical process. The result is wafers of silicon with a surface roughness of less than 1/1,000,000th of a millimeter. Buffed to a sheen, they're finally ready for etching with the circuit design. Coming up, how do they eliminate the biggest enemy of manufacturing in a microscopic environment, the common dust particle? Find out next on How Do They Do It?
So this is a graphic out of the book. It shows the basic processing of making computer chips. So you start with a single crystal on the top, and then you slice and dice it. You polish one side of the wafer, typically, to a very high level and a very smooth mirror finish. And the back side, you don't polish as much. So we call it single polished wafers. And you make all the computer chips on the polished side. So once you have a starting material, you can go ahead and put different layers of materials on there. So you might have some insulators and some conductors. And then at each layer, you have to pattern and etch the pattern into that layer. And then you build one layer on top of another, on top of another, on top of another, until you get a final computer chip. So to transfer the pattern from a design onto the wafer, you use a process called photolithography. Okay, and that's basically you prepare the surface with a photosensitive material, and then you project the image onto the photosensitive material, develop it. You're left with a pattern that's the same as what's on your mask or your design. And then you etch what's exposed. You remove the photoresist, put a different material, the next layer down, and then repeat the process. So that's why you have this circular thing here. So you prepare the silicon wafer, you put the photoresist on it, right? You project some light through your mask. Your mask is defined by your design. It's kind of like a CAD file. And we'll go through these steps in a little bit more detail. So this is a mask. You project it onto the wafer through a lens system, right? You usually do one chip or several chips at a time. You don't do the whole wafer. Once you expose the photoresist and develop it, okay, you can go ahead and etch what's exposed. Then you remove the photoresist, okay, and then you put another material on there, and then you start over again. So this cycle goes, this cycle goes around and around and around for each layer. And then once you're done and you have your chip completed, you need to connect it to the outside world. So you do that with bonding and with wire bonding. So you connect wires to the chip, okay? And then once you do that, then you package it. And once it's packaged, then it can go into circuit boards, okay? So that's the basic idea. And of course, we start with crystals. We talked about crystals in the other lectures. So you can see the crystal structure of silicon, which is a diamond structure, okay? So it's a diamond type lattice. And then if you look closely at the different planes that are defined within the crystal structure, you can see we have different planes depending on the orientation of the crystal. So you can make different wafers with different planes that are on the surface. The most typical one is the 100 plane, which you see on the left side, okay? And then less common is 110 and 111 crystal orientations, but you can buy wafers with those different orientations, and the way they make it is they orient the seed crystal differently, so that surface, that cross-sectional surface when you slice that crystal is whatever plane you want on the surface. And each surface, each orientation has different electrical properties, mechanical properties, right? And also etching and process properties. Okay, and we'll talk a little bit about that in a few minutes. All right, so this is one way to cut the silicon wafers. You can use an electroplated bandsaw to cut the ingot into slices. More common now, I believe, is using a diamond encrusted wire. Okay. They typically polish the side of the ingot, which is the single crystal, also known as a boule, to get it nice and smooth. And then they oftentimes will put a flat on one side, and that helps the machines orient the wafer in a certain crystallography direction. They also now put in notches instead of flats because you lose some surface area when you make a flat. The older wafers, the ones that are less than 8 inches, generally have a flat that indicates what the orientation of the wafer is. Okay, we slice and dice it, right? We grind the edges of the wafers so they're smooth and not sharp, no sharp edges. We polish one side to make it very flat. Okay, and that's done with chemical mechanical polishing. So it's a combination of a fine slurry grit. And usually they put some chemicals in there to help smooth it out and etch it and give it a smooth finish. Now these are the older wafers shown here, and you can see that the flats give you an idea of what the orientation is, which way is up, right? And then they have secondary flats, which gives you other information as to what crystallography orientation was created during the making of the large crystal. Okay, and we typically use 100. There are P and N type wafers, and that's the doping that they put into the crystal itself. And that's to aid the electronic manufacturers primarily, because they'll have N and P type transistors. So they have one less step in the process in terms of doping the crystal itself. And so they start with either N or P type. And then you can see this is a 100 wafer, which means that the 100 plane is on the surface of the wafer. Okay, and it kind of shows you where the other planes are. All right. I'm not sure. This is 6 minutes. Oh, we could probably watch this. You guys want to watch another video? Or should we wait? Yeah, everybody's saying yes. All right, hopefully this will work. I'm going to stop share. First, I'm going to go here.
In this phone, there are nearly 100 million transistors. In this computer, there's over 1 billion. The transistor is in virtually every electronic device we use. TVs, radios, Tamagotchis. But how does it work? Well, the basic principle is actually incredibly simple. It works just like this switch. So it controls the flow of electric current. It can be off, so you could call that the 0 state, or it could be on, the 1 state. And this is how all of our information is now stored and processed in zeros and ones, little bits of electric current. But unlike this switch, a transistor doesn't have any moving parts, and it also doesn't require a human controller. Furthermore, it can be switched on and off much more quickly than I can flick this switch. And finally, and most importantly, it is incredibly tiny. Well, this is all thanks to the miracle of semiconductors. Or rather, I should say the science of semiconductors. Pure silicon is a semiconductor, which means it conducts electric current better than insulators, but not as well as metals. And this is because an atom of silicon has 4 electrons in its outermost or valence shell. And this allows it to form bonds with its 4 nearest neighbors. Howdy-ho there. What's up? So it forms a tetrahedral crystal. But since all these electrons are stuck in bonds, few ever get enough energy to escape their bonds and travel through the lattice. So having a small number of mobile charges is what makes silicon a semiconductor. Now this wouldn't be all that useful without a semiconductor's secret weapon, doping. You've probably heard of doping. It's when you inject a foreign substance in order to improve performance. Yeah, it's actually just like that, except on the atomic level. There are 2 types of doping, called N-type and P-type. To make N-type semiconductor, you take pure silicon and inject a small amount of an element with 5 valence electrons, like phosphorus. This is useful because phosphorus is similar enough to silicon that it can fit into the lattice. But it brings with it an extra electron. So this means now the semiconductor has more mobile charges, and so it conducts current better. In P-type doping, an element with only 3 valence electrons is added to the lattice, like boron. Now this creates a hole, a place where there should be an electron, but there isn't. But this still increases the conductivity of the semiconductor because electrons can move into it. Now, although it's the electrons that are moving, we like to talk about the holes moving around because there's far fewer of them. Now, since the hole is the lack of an electron, it actually acts as a positive charge. And this is why P-type semiconductor is actually called P-type. The P stands for positive. It's positive charges, these holes, which are moving and conducting the current. Now, it's a common misconception that N-type semiconductors are negatively charged and P-type semiconductors are positively charged. That's not true. They are both neutral because they have the same number of electrons and protons inside them. The N and the P actually just refer to the sign of charge that can move within them. So in N-type, it's negative electrons which can move, and in P-type, it's a positive hole that moves. But they're both neutral. A transistor is made with both N-type and P-type semiconductors. A common configuration has N on the ends with P in the middle. Just like a switch, a transistor has an electrical contact at each end, and these are called the source and the drain. But instead of a mechanical switch, there is a third electrical contact called the gate, which is insulated from the semiconductor by an oxide layer. When a transistor is made, the N and P types don't keep to themselves. Electrons actually diffuse from the N-type, where there are more of them, into the P-type to fill the holes. This creates something called the depletion layer. What's been depleted? Charges that can move. There are no more free electrons in the N-type. Why? Because they've filled the holes in the P-type. Now this makes the P-type negative thanks to the added electrons. And this is important because the P-type will now repel any electrons that try to come across from the N-type. So the depletion layer actually acts as a barrier, preventing the flow of electric current through the transistor. So right now the transistor is off. It's like an open switch. It's in the 0 state. To turn it on, you have to apply a small positive voltage to the gate. This attracts the electrons over and overcomes that repulsion from the depletion layer. It actually shrinks the depletion layer so that electrons can move through and form a conducting channel. So the transistor is now on. It's in the 1 state. This is remarkable because just by exploiting the properties of a crystal, we've been able to create a switch that doesn't have any moving parts, that can be turned on and off very quickly just with a voltage. And most importantly, it can be made tiny. Transistors today are only about 22 nanometers wide, which means they're only about 50 atoms across. But to keep up with Moore's law, they're going to have to keep getting smaller. Moore's law states that every 2 years, the number of transistors on a chip should double. And there is a limit. As those terminals get closer and closer together, quantum effects become important and electrons can actually tunnel from one side to the other. So you may not be able to make a barrier high enough to stop them from flowing. Now this will be a real problem for the future of transistors, but we'll probably only face that another 10 years down the track. So until then, transistors, the way we know them, are gonna keep getting better.
All right, so I like this video. It's a little goofy the way it looks, but it explains how a transistor works really well. So it gives you an idea what's meant by N and P type, and then how you can create a switch electronically. So you can turn it on and off really, really fast. Okay. We still got about 3 or 4 minutes left. So we're going to go ahead and continue for about 2 or 3 more minutes, and then we'll call it a day. So a MOSFET is a metal oxide semiconductor field effect transistor. Okay, so we're going to talk about how those are made. In fact, now that I'm thinking about it, I think we're just going to call it a day.